All right, so I want to wrap up everything on transformers, mutual inductance model. Don't want to talk about that. Just a quick summary. These are posted on the Canvas page in the before version. The ideal transformer. What makes it ideal again? Say that again.
Same direction.
No leakage flux. That's the thing I'm really looking for, right? No, that's what makes it ideal. To get no leakage flux, what do I have to have no leakage flux? Permeability is basically infinite, means the reluctance is basically zero, right? The directionality of the current could be whatever. We typically just do the directions of the current that way, right? That's just kind of our standard approach for a two-port network, all right? If I do it that way, then I get the relationships I have here. So I relate the magnitudes. Again, I don't really focus too much on testing you on figuring out the right polarity. The way I think of it is into the dot one side, out of the dot the other side, okay? Then for a real transformer, making it real meant that we basically let the permeability be something non-infinite, which when we did that, we ended up with this model. This model has no losses yet, right? There's no losses here. The leakage represents what? So this leakage here, what does that represent? It's a result of the current. What's it represent kind of on the fields view of this thing?
It's like the leaking field there. It's not like
Yeah, it's basically it represents the impact of basically field that is not linking the other coil, right? So if that leakage was zero and I put a voltage right here, what would happen is if the leakage was zero, this would basically be a short right here. What would happen is all the voltage that I was applying would cause a current into the magnetizing inductance. That's the field that's represented. And then effectively the ideal transformer represents the coupling over to the other coil. Okay. The fact that there is some flux that doesn't link the other coil means that the voltage I apply here doesn't fully create a field inside the core. That's basically what it represents. So ideally, which one is bigger, L-mag or L-leak? L-mag. L-mag should be much, much bigger than L-leak. All right. And as a result of that, if that's really true, right? If I think of this thing as a voltage divider, most of this voltage that I apply should appear across L-mag. Okay. And if L-mag itself, in general, here's L-mag. Tell me what the value of L-mag. What should it ideally be? So this is our formula for it. The number of turns squared over the reluctance of the core. Ideally, what should that be? You tell me. So what's the property of the material that we wish to be infinite? Well, you get the right idea, right? So this was our formula for reluctance, right?
Like the overall reluctance versus the RC,
So in general, the reluctance of the core when we're talking about it would be, you know, whatever the combination of all the elements of the core would be. So whatever the equivalent, if I think of that magnetic circuit as just a resistive circuit, our core is the equivalent resistance combining of all. So what I'm saying is usually you can reduce that down to one number. And if the core has an infinite permeability, mu, which is like the conductivity of a conductor, what should be true about the reluctance? Should be zero, right? And so L-mag ideally should be approaching infinite, should be a really big number, right? And ideally it would be infinite, right? So that tells me that the current down this branch should be pretty small. So we've talked about that a little bit. Now, when I include the full model, I basically get this. The full model, this is with losses. So R core, RP, and RS, those are resistances. What are RP and RS? What do they represent physically? Yeah, the resistance of the windings, yeah, the actual windings. And then the core represents the fact that the core heats up when this thing is working, right? And it represents the fact that there's hysteresis and there's all these things that are happening inside the core. All right, then we talked about the fact that I have this impedance reflection property. So if I have an ideal transformer and I put an impedance on the secondary side, I can reflect that over to the primary side and basically convert this circuit into this circuit. Right. So basically from the perspective of the terminals, they're equivalent to each other is basically what we're saying. All right. And so I have the turns ratio to do that. Now, if I was trying to reflect something from the primary to the secondary, what would I do? Yeah, basically flip that formula, right? Yeah, N2 over N1 squared, right? So then I introduced these approximate models, where basically what I said was, I started with this model right here. And I could, what's the difference between the model I'm showing right here and the one that I'm showing on the top right there? There's two things that are different.
You two things in parallel all the way to the left and see what's over.
Yep.
Into
Yeah.
secondary.
Yep. So I moved this stuff here out to the front, which, you know, if you did that in circuits 2 or whatever, you would have gotten that wrong, right? What we did basically is we're saying that the current, really the voltage drop across these two guys is so small that it's entirely equivalent, not entirely, but it's almost equivalent to moving that thing to the front because there's so little voltage drop across those guys, right? It's basically the result of that. And we did an example that kind of proved out that that's feasible, and that's feasible in most cases. And yes, I reflected over these parameters. Then what we said is if the circuit's loaded, because this current I sub E, the exciting current, the current that's required to make a field go through the core, because that current's so small relative to the current going into this guy, I basically could remove it. All right. At least when the thing is loaded, meaning that there is a lot of current, basically the rated amount of current flowing through the transformer. In that particular case, I can get rid of it. All right. And then this guy simplifies down to sort of a relatively simple model. Okay. All right. Now, what we can do is, and you're going to see this in the homework a little bit too, is I can refer the parameters of the transformer to either side of the transformer. Right. So I did everything here with a 1, meaning it was referred to the primary. I can transfer them over to the secondary side. If I know the parameters on the primary side, how do I get them to the secondary side? So this is XM1, this is XM2. How do I get that XM1 to XM2? How would I calculate XM2? Yep. So I multiply like that, right, by the turns ratio. Similarly, if I give you the parameters on the secondary side, you reflect them over through the opposite of that. Okay.
So this ratio squared, does it work for everything that we want to reflect over? So all you do is take the turns ratio squared?
Yeah. You've got to remember which way to apply the turns ratio squared. Well, I mean, so is it N2 over N1 or is it N1 over N2? Right. That's basically the deal. All right. So that's kind of all I need to know, but I want to talk about some practical issues. Now, most of the time, you know, these are all single phase transformers. You look at most transformers that are out there in the world, they're usually 3-phase transformers. And 3-phase transformers are a bit more complicated because you can have what? Well, you can have a delta connection on one side and a delta connection on the other side. You can have a Y connection and a Y connection, or a delta and a Y, or a Y and a delta. So there's a lot of ways to do that. I'm not going to talk about that stuff. It's a little more complicated, right? But I do want to talk about a little bit of the way that we would look at these in the utility system, right? So we often tend to talk about things in what we call the per unit system. All right. So we talk in terms of percentages. And I gave this example the other day, right? Where we see this a lot in motors and in power system applications. So what I've got here is basically, this is a screenshot from an automation system of some kind, basically an automation system that is meant to power, you know, a large bank of motors. And I zoomed in on a section of that. So here is a section. There's two motors there, HM, hammer mill motors is what they are. We're gonna start talking about motors next week. But basically, inside these things, that these guys are rated for a particular power, and they're rated for a particular horsepower value. Okay, and what I have here is, as an example, it has this percent FLA. This is a pretty common thing to do on a motor, but it's basically percent of full load amps, because the motor is rated to operate at a particular amp number. If I get a 200 horsepower motor, a 400 horsepower motor, they're going to have different numbers. And it's inconvenient to be talking about, well, if a motor is rated for 100 amps, you really don't want it to go above 100 amps. That's not a good thing, because what's going to happen if I'm going over 100 amps if it's rated for 100 amps? I could burn it out, right? Basically, that's my primary concern. So what I want to make sure of, now, why would that happen with a motor, that it would go above that? Well, if the motor gets jammed up for some reason. All right, this guy is a hammer mill, so you can imagine he's hammering, right? He can get jammed up. If he gets jammed up, he's just going to keep, and we're going to learn why this is, but he's just going to keep jamming more and more and more and more current into it until he starts to break free. At some point, the thing's going to burn up or break something pretty badly. All right, so if the number is, let's say the motor on the left, for sake of argument, let's say this guy was rated for 100 amps, and this one was rated for 200 amps. If the readout said on one side 86 amps and the other one said 122 amps, it's just not very clear what that means in a general context. So usually we just talk in terms of the percent of the rated value. Does that mean no matter what the size of the motor is, the percent value means something to somebody? All right. So it's pretty common for us to do that. So that means we have to normalize the values. So if the full load amps is 100 and this guy is at 69% FLA, that means it's 69 amps. So we just have to normalize somehow. So we got to figure out what that normalization is. And when we do that, we use per unit. Okay. So in the per unit system, what we do is we define for the power system that we have a base power, and we use a base apparent power. All right. And then what we do is we define a base voltage, and then we get a base current using the base power and voltage. Oops, that should be V base right there. And then essentially I use Ohm's law to get a base impedance. All right. So it's a little bit weird, but I want to go through an example of that. And I talked about this the other day in the context of the distribution system. Right. And the types of problems where I would use this would be like, okay, if I have, I said this would be like the wooden poles that are carrying power throughout a region. This is a map of what that might look like. All the different colors there represent a different circuit somewhere in the network. All right. Each of those circuits is basically just a bank of, in this particular case, 24 kV voltage that's the 3 wires running overhead. And then there's transformers on the wires there that carry it down to a 240 volt. Okay. So usually there's 2 types of transformers in these systems. Usually, there's the overhead cans. So when you see like a grayish can on a pole, right? You look up and you see a can hanging up there. That's a transformer that's taking power down, or the voltage down, from whether it's 13,000 or 24,000 kV. Sorry, not 24,000 kV, 24 kV or 13 kV down to just, let's say, 240 volts. Or what you see is a pad mount transformer, which are those green boxes that are on the ground. All right. And which one you have depends on whether it's an overhead system or an underground system. And the example I gave here, it says, okay, well, here's a transformer. This is a diagram we use in one-line diagrams, which we'll talk about a little bit later. But basically what I see here is that apparently I have 9 customers, and it says my total load is 54 kW. So this is probably like a 60 or 75 kW transformer, something like that. Okay. That's not to say that's what the load always is. That's to say what the peak load is. Okay. All right. So in these systems, all right, so here I've got a pole mount 25 kVA transformer, and I took all of the data from that transformer to see what we typically see when we're looking at these. the ratings we get, so I see the capacity, it tells me is 25 kVA. That's the total amount of power this thing should process. And they're not meant to deal with different levels of voltage, right? So it was rated for, it says here, 7620/13,200 volts. And the secondary side voltage is 120/240. Okay. So what does that mean there when it says, so 7620/13,200? What do you think that is if I try to, what number relates 120 and 240? You understand what number relates those two? How do I get from 120 to 240? Multiply by 2. Yeah. How do I get from 13,200 to 7620? Harder question. Square root of 3, right? The primary side of this guy would be 3-phase. And I could hook it up to apparently line to line or line to neutral. Okay. Typically on the secondary side, what you have, it says line neutral. Just to be clear, we're not going to deal with this, but if you're interested in it, that secondary side, what that means is the secondary side is itself a transformer. What they do is they quote unquote center tap it. So right in the transformer we'll look at Monday is center tapped, right? So what they typically are doing is they're grounding the middle of the winding, which means that effectively there's a transformer itself on the secondary side where half the number of turns on the secondary has half the voltage on the secondary. So this basically from here, I would have 120 volts. And here I would have 120 volts. So between, and they call this line, and neutral. And so what you would see is if I went from one line to the other line, I would have 240 volts. Okay. So anyway, that's how that goes. And you can see a bunch of different things on here that are important. It's rated for 60 hertz, right? It says it has a certain temperature rise. That's how much warmer it's allowed to get. Okay. It says some other stuff here about how it's cooled and all that kind of stuff. Now, the other thing it tells me here is two values that we'll look at. It tells me an efficiency at 100% load. All right. So an efficiency is one of the problems on the homework. I don't remember which one it is, but I have you guys dealing with an efficiency, right? Obviously, I want this thing to be 100% efficient if I could. All of the power going into the primary, I want to go into the secondary. I don't want the transformer to get too hot, but it has some. Now, the other thing it tells me here is that the impedance is 3%. Okay, which is weird, but that's generally the way that the impedances are written, and that's using the per unit system. Okay, where everything's done as a percentage. All right, and there's standards associated with how these things are rated here. All right, and so anytime we deal with this is when you get into power stuff, generally speaking, there's standards. So if you buy a transformer from ABB or you buy a transformer from Eaton or Schneider or whichever company, they generally should be the same. They're commodity products. They should basically be the same thing. There's really nothing particularly special about a transformer. And the utility expects them to meet certain standards, so they've adopted standards. And if you want to sell them, you got to meet those standards. Okay. So let's look at an example here. So if I'm talking about a power system, so like in other words, if I was talking about, in this case, a power system, let's say I'm talking about the 9 homes that are connected on the secondary of this guy. All right. And let's say they're fed from this transformer, a pad mount. It's cut off here a little bit, but it says a pad mount. So a pad mount would look like this. And if you see a number like that written on the side of them, now you know what that means. That means it's rated for 50 kVA. All right. So in this particular case, this guy is rated for 50 kVA. And the way I'm going to say this guy is hooked up, so this was a little bit confusing, but I'm going to say he's connected up to the 13,200 on the primary and 240 on the secondary. All right. So what I'm going to do is I'm going to say, let's figure out what our base value is. That's the value we normalize everything to. So if everything connected on the downstream side of this transformer was operating at 100% load, right? If 100% load was being drawn from this thing, that would be the base power. So if I was operating at 100% load on a 50 kVA transformer, what do you think the base power is? that I would normalize everything to. If he's operating at 100% power, that would be 50 kVA. So if he's operating, if I'm having 50% of the power drawn from this thing, how much is being drawn from it? 25 kVA. All right, so it's just easier to think in that context. I don't need to know anything about the specifics of that thing, whether it's a 25 kVA or a 50 kVA. The fact that it's 50% means something to me. All right, so the primary base voltage in this case, if I'm saying that it's hooked up to the 13,200, which means that it was hooked up to the Y, then I would say it's 13,200 volts. And the secondary, I'll say is 240. In your homework, I give you basically, I don't have a three-phase like that, so it's less, it should be more clear. All right, how would I figure out then the base current, which is the maximum current this thing should provide? Divide what? Yep. So basically I would say S base divided by V base is I base. All right. So if I can do this for both the primary side or the secondary side. So if I do it for the primary side, in this case, I end up with 3.7879 amps. That means that if this transformer was operating at 100% load, there would be 3.7879 amps going through it. If it was 50% load, it would be half of that. All right, on the secondary side, how can I figure out I base secondary? I got two ways to do it that I can think of. I can use the current ratio, right? I can use the turns ratio, the 13,200, 240. I could use that, right? So again, I'm never given the turns ratio. The voltage ratio should be basically the turns ratio. So I could use the 13,200 over the 240. If I'm relating currents and voltages, and I'm not squaring anything. When I'm relating impedances, then I have the turns ratio squared, right? So I could use that. I could also basically say S base divided by V base secondary would give me I base primary. Or sorry, I base secondary. Right? If I went through, they should be related by the turns ratio, right? I could do it either way. So this would be primary, this would be primary. So if I do that, which one is going to be bigger? Is I base secondary going to be bigger or smaller than the primary? Is what? To be higher on the secondary, right? Because there's more current on the secondary side. The whole reason we're using these transformers basically is so that we're not pumping huge amounts of current over long distance. Like this pad mount transformer is connected to 9 houses. So, I'm comfortable with it having a ton of current and getting the voltage down to a nice sort of safe level so that I'm not so concerned about having it in my house. All right. So if I have high current, why does high current bother you if you're going down a long distance? Heat, right? I squared R, right? At some point, I got to get the voltage down to a safe number. So I get it down to a safe number once I'm, down to the level of 9 houses or 5 houses or whatever, right? So in this case, if I do the math, it works out to be 208 amps. Right, something like that. Okay. Now, to get Z base, how did I get the Z base? How would I get the impedance base? Yeah, I got basically V equals I times Z, right? So V base is equal to Z base times I base. And so on the primary side, so let's think about this. Which one's going to be bigger? That may be less clear. Primary side is going to be bigger. Yeah, so this guy works out to be 3.4848 kilo ohms. Now, to do it on the secondary side, I can use that same thing, V equals I times Z, but I can also use what to get to the secondary side? Turns ratio squared if I'm doing an impedance transformation. So it's going to be a lot smaller. This guy ends up being 1.152 ohms, all right? ends up being quite a bit smaller. All right, so now how would we sort of use this? And I want to talk about, so we're going to do a problem with this, but I want to get at this other issue of, so it's got a bunch of data on this transformer that I pasted in here. One of which is, says the impedance is 1.67. Now, what does that mean? That's the internal impedance. It's what it's told me, like just like it did here. It gave me the impedance. It's telling me that the percent Z is somehow equal to 1.67%. So what has it told me with that? All right. So once the transformer is under load, we've talked about this before. So here's what our, well, let's talk about the percent Z a little bit more. Here's what the transformer model looks like, right? Under load, which impedances mattered? Which ones do we say mattered under load? The leakage ones, and these ones, these resistances in series. It should be the case that the current through here is really small because these impedances are really big. All right. What they're telling me is basically under load, they're telling me the values here in this model. They're telling me somehow REQ and XEQ, which is the combination referred to one side of the resistances and the leakages. So when I say the combination, like it's telling me the primary side resistance plus the reflected secondary resistance. Never separates those two. It always tells them to me together. All right. And I can move them to one side or the other. Okay. So somehow it's telling me that. All right. So what it's telling me is that from the perspective of this transformer, here's the ideal transformer. Under load, this guy can be thought of like this, where this is REQ and this is XEQ. And those REQ, XEQ, it's that combination of stuff. Okay. So here's V2, here's V1. If I think about this impedance here, how would I combine those into one Z equivalent? Well, those are two resistances or two impedances in series, right? So what would the formula be for the two of them in series? So if REQ and XEQ, let's say ZEQ is the combination, the series combination of those two things. What would the series combination of those two be?
Like A plus JB.
Yeah, you'd say REQ plus JXEQ. All right. So I talked about the magnitude of those. The magnitude would be this, right? What it's told me is that it's told me the value here is 1.67% of Z base, right? Is what it's telling me. So when I'm on the primary side, the way I drew this right now, where those impedances are on the primary side, I'm saying that the magnitude of the impedance is 1.67% of what is 3.4848 K ohms. So the magnitude of that impedance is what it's telling me. Is 1.67% of that. All right, so it's should be a pretty small number. Okay. So it's telling me the magnitude of the impedance, but it's not telling me anything about the real part and the imaginary part, right? So sometimes, most of the time, in fact, I don't really need to know that information. But if I do need to know that, I can go to typically, again, these are standard values. There's an IEEE standard that you define for transformers. And so what it tells me here is for different single phase transformers like I have in this power system. It tells me here's the kVA rating. So for a 50 kVA transformer here, what it tells me is that the percent impedance should be somewhere between 1.2 and 6.4. And that's what it was in this case, was 1.67, so it's in that range. And then it tells me the X over R ratio is apparently 1.6. So what has it just told me? So if it's sure. So if I have ZEQ equals REQ plus JXEQ, right? I have right now, I know what the magnitude of ZEQ is, right? And it's told me the ratio of these two values. So if I know the resistance, I can figure out the reactance, whatever, I can either way. But that can also, how can I relate that to potentially trying to figure out what REQ and XEQ are? How can I use that ratio to figure out those components?
Instead of having like the two very different variables under the square root, you can substitute. Using the ratio, you can substitute the other one in, so you just have one variable, solve for it, and then use the ratio again to find the other one.
I guess you could do that. Yeah, I hadn't thought of it that way. You could. Okay, you could say that, okay, so I wouldn't want to do it that way, but you could. So you could say this. Yeah, it's a smart idea.
That might not be practical.
No, you could do it. And then you could solve for an R value. The way I thought about it, the way I think about it is that if I have a vector R plus JX, right? If I told you, give me the angle of that vector, how would you get the angle of that vector? Yeah, you get tan inverse of X over R, right? That's equal to the angle of the impedance. Once I have that angle of that impedance, I can say that REQ, how would I figure out that? Well, I'd say it would be the magnitude of Z times what? If I have a vector, how do I get the real part of a vector if I know its magnitude and I know its angle? Cosine. I like that rather than square rooting and stuff. I don't know why. But yeah, so that's a reasonable way to think about it too, right? So if I said that for this particular transformer, let's say that X over R is equal to 1.6, and we know that the percent ZEQ is 1.67%. All right. How do I figure out for myself what I have for, let's say on the primary side, so let's say I've got it set up like this. All right, here's REQ, I'll call it 1, XEQ 1. Well, so I'm basically saying, based on standard values, IEEE standard values, I came up that it's 1.6. I would give you a number like that probably, right? So I've got that ratio is 1.6. Here's V1. Here's V2. I want to figure out what REQ1 and XEQ1 are on the primary side. So if I know ZEQ is 1.67%, then what I would have to say is the actual magnitude of ZEQ. How would I get the actual magnitude of ZEQ? So I'd say it's 1.67% times Z base primary, right? Whatever I have on that side. That'll give me the actual magnitude. So let's say I wanted to figure out REQ and XEQ. And I'm writing 1 here, the subscript 1, because I'm saying I want to figure them out referred to the primary. So I basically just go through that formula that I just did, right? I basically say that it would be, what was the formula we did? We looked at this. Where did I do that formula? Here's where I did that formula, right? So I basically said I could figure out the angle of the impedance, and then I could find the real part of the impedance, right? So that's basically what I'm doing here is I'm saying REQ1 would be whatever I get for the actual ZEQ up here. Multiply that by the cosine of the angle, which we said was the inverse tan of 1.6, like that. And then same for XEQ. Except what would I use for XEQ? Sine, yeah. And inverse of 1.6. So in this case, if I do this on the primary side, I get that REQ1 is equal to 30.8439 ohms. And I get that XEQ1 is 49.3502 ohms. Like that. All right. Now, I could also represent the transformer like this. Here's V1. Here's this, where this would be REQ2. And this is XEQ2. And here's the secondary side. I can refer the parameters either side. So I could figure those out now by doing what? I could do the turns ratio squared thing. I could use the impedance reflection with the values I just got, REQ1 and XEQ1. I could do the turns ratio squared thing and do the impedance reflection. Or how else could I figure these out? I could figure out what ZEQ is on the secondary side, right? What would that be? Well, it would be 1.67 times Z base secondary, right? Figure out whatever that is, right? And I'm going to end up with, if I go through that process, which one's, so let's ask ourselves, which one's going to be bigger and which one's going to be smaller? Is the primary side resistance going to be bigger or the secondary side resistance going to be bigger? Primary side resistance is going to be a lot bigger, right? Why would I want the secondary side resistance to be smaller? There's a heck of a lot more current over there, right? And so it does work out to be. So this guy is actually 0.0102 ohms, right? And this guy works out to be, so I'm going to call it, sorry, not RS, REQ2. And this is XEQ2. And this is 0.0163 ohms, right? So we're talking, these guys are 10 milliohms sort of thing, right? So as opposed to tens of ohms on the other side, right? But there's a heck of a lot more current on this side, okay? All right, so now where would I use this, right? So here's an example. Let's say I've got this 50 kVA transformer and I have this load here connected to the secondary side, all right? And I want to figure out, let's say, what is I1, all right? So I want to figure out what's the current going into the primary side of this transformer. So how should I approach solving a problem like this one? What's the easiest way to solve this given what we know now? I've told you what ZL is. How should I transform this circuit here? If I want to figure out I1, how should I do that? What's the simplest way to find I1? Yeah, and so what impedance should I use here? V1 over what impedance? Z load reflected over. So basically to do that, I gotta modify the circuit, right? So the circuit, in other words, the circuit I'm showing on top is equivalent to this circuit where I have REQ, XEQ, and the reflected impedance, right? Where this impedance is ZL times whatever the turns ratio squared is. And what's that gonna be? So what over what to reflect it from the secondary to the primary? Yeah, so in this case, it's gonna be 13,200 over 240. That's the turns ratio, right? Squared.
You always assume 240, we're just given, V1.
You would be given, well, it was, so the transformer was rated, so for this particular transformer, I would have told you, I'm using the transformer I talked about, so I would have told you a voltage ratio. And so for this, how would I solve for I1? Well, super easy, right? What do? I basically say that I1 would basically be V1 divided by the total impedance in that circuit, right? So the transformer is rated for 50 kVA, but it has this impedance. So that impedance is dictating what the current is, right? I mean, I could have an impedance of 0 here. If I had an impedance of 0, there's gonna be a heck of a lot more than 50 kVA going through that thing. It's rated to give 50 kVA, but I can operate it lower than that, right?
Value.
No, what happens if I put no load on it? If I leave it open circuited on the secondary side, then how much current's flowing? 0, right? That's okay. That's the rated current. If I do 50 kVA divided by the voltage, that tells me the rated. We typically want to operate, and it's a good question. It's typically we want to operate at a fraction of that rated value. I don't want to go above 100% of the rated. So if I did 50 kVA divided by 13,200, I would get 3.7 or whatever we got, right? That's to say that's the maximum you really want to ever get it to. Maybe you can overload it a little bit for a little while, but not for too long. All right, so the current in this case would be whatever that ZEQ is, right? So I would put in the numbers I calculated for these guys. So when I say ZEQ, let me be more clear that, yeah, REQ plus J, and this was on the one side, the XEQ1, plus that ZL times 13,200 divided by 240 squared, okay? If I go through that math in this particular case, I end up with this being 3.7836 minus J times 1.524, like that. And if I do the how would I convert that to a per unit current? Sometimes I want to put that in per unit. Let's say I wanted to do that as I1 per unit. How would I get that to a per unit current? Basically divide by the base current to give me what's the percentage of the total that it is. So we had found that I base primary. So that on the primary side, the base current was 3.7879 amps. So if I divide, basically I say what's I1 divided by whatever the base on the primary side is. This guy works out to be 0.9989 minus J times 0.4072. If I take the magnitude of that, it works out to be 1.01, like that. So what's that telling me? If the magnitude of that current is 1.01 in this per unit system, what's that telling me? Well, that's what I'm asking you. Right?
What does that represent, the I1 PU?
So it's in this per unit system. So what I'm saying is that the total current is apparently this. I'm dividing by the base value. Basically what I'm doing is I'm normalizing. I'm saying the rated current that I have on the primary is 3.78. I divide by that rated, I divide the current that's actually flowing divided by that rated value, and I get 1.01, which means that I'm drawing 101% of the rated current. Right? If I had taken I1 and divided it by the rated current, the base current, then I would have, and I got 0.5, that would have said that I'm running the thing at 50% of its rated value. So in the, and if you look at any time you're in the power system, that's all they ever really talk about is per unit values. They never talk about the actual amps, whatever. They say, you know, you're running at 90% rated or 60% rated or whatever. So in this case, I'm running at 101% rated. All right. And if you take power systems, you know, that's what they always use. Okay. All right. So that's the last I have to talk about transformers other than whatever we'll do on Monday. Okay.